Thank you. So today we're going to talk about lithium-ion batteries and how to prevent thermal runaway, specifically in applications like energy storage and data centers. And we're going to also touch a little bit on the best practices for a system design. Back in February of this year, we made an agreement with a company called Nexeris. As you probably know, Honeywell has an advanced smoke detection system, which is the VESDA system through Xtralis, that can predict or see fire when it's still invisible, and be able to alert and mitigate the risk that can come from fire. Unfortunately, we do know from testing, since the VESDA system can also have gas detection integrated. We also knew that we are unable to stop any lithium-ion fires because of the several testings that we've conducted. And by that I mean the conventional type gas detection will not stop the thermal runaway, and I will explain that during my presentation. So we went to a company called Nexeris, and they have developed this unique technology for the US Navy on how to detect lithium-ion off gases in order to prevent thermal runaway, and it was a perfect match for us. So we've had this alliance together since February, and ever since we've been taking this worldwide to them. In today's presentation, this is not going to be based on a sales presentation or anything. It's just facts and what we need to monitor for off gases in order to prevent thermal runaway. So the energy storage industry is rising. This is where we are today, and this is where projected to be. This is continuously rising, and California is actually one of the states with Hawaii that are actually leading the country. So by 2050, 33 states are committed to be 100% independent of fossil fuel. So that means millions and millions of batteries in each of those containers that are going to be installed. When it comes to the data centers are also being converted. This is where we are today, and the blue is how much percentage you have in regards to the total, number 6 here, in regards to lithium-ion batteries. So we're at 10%, and in the next 5 years, all data centers are going to be approximately 40%. So what do I mean by the percentage? Right now we use lead acid type in data centers, but because of the rise of electric cars and because of how economical these lithium-ion batteries are becoming, it's becoming more and more economical to use lithium-ion batteries in data centers as well. We deal with companies that dominate the data center industry worldwide, and they are telling us that they're switching a lot of them into lithium-ion batteries. So as you can see, it's going to be 40% in the next 5 years, according to Bloomberg. Now that being said, the existing data centers are the ones that are also being replaced on a monthly basis. And the authority having jurisdictions up in New York discovered that every contractor was sending a permit, requesting a permit to do the change, and they were just simply marking like for like, meaning they are replacing the lead acid type with a like for like. And when they discovered they were lithium-ion batteries, they're like, this is not like for like. So they put a big stop on that, because lithium-ion batteries have the potential of exploding, and we're going to discuss that. So just a little bit of background on the lithium technology in general. So it's the third element in the periodic table. Today we have our devices using lithium-ion batteries. You're probably, if any of you is watching this on a laptop, you're using a lithium-ion battery. So in general, they're very safe. They do have quite a bit of advantages. They charge much faster than any other elements. They hold much more energy than the other elements in the periodic table. And at the same time, they can last much longer in terms of cycle count. Now, what do we mean by cycle count? Cycle count is if you charge your device from 0% to 100%, this is considered one cycle. If you charge your device from 50% to 100%, this is considered half a cycle. So lithium-ion batteries are known to last much longer than lead acid type. This is why you can carry your phone probably an entire day without charging it, depending on how much you use your phone. And that's what is meant by cycle count. And then finally, it's also the lightest of all metals, which means you can use lithium-ion battery. It's very light. You can carry on your devices, and it's not too heavy. However, there are some limitations with lithium-ion batteries, and the industry is always building around those reputation in order for us not to have accidents and explosions. So what are these limitations? You will see in the coming slide the chemistry of the lithium-ion battery itself. There's a separator inside, and because the battery is very fragile, we have to build a very strong casing for the battery, because if you accidentally bent your phone, then your phone will explode. And that did happen on one of the major airlines here in the US, where somebody dropped his phone between the two seats, and he tried to get it, and in the process he bent the phone, and it was an immediate thermal runaway. So the industry has to protect the devices against an explosion. So they're very fragile. They also have to protect it in the operating system itself. You cannot keep charging a lithium-ion battery. If you do, it will explode. As you've seen with hoverboards, most of the time it's manufacturing defect in the battery. It keeps on getting these charges, and then eventually it will go into thermal runaway. So we build the operating system to prevent overcharging and discharging as well, which can create thermal runaway conditions. And that's when the software shuts down the charging when you're charging, and then shuts down the device when you're discharging, so this way it doesn't go into thermal runaway. Overheating is a problem, so for that reason it's temperature sensitive. The device is shut down automatically. And then finally, the industry is not fully mature, and we're going to come back to that. The manufacturers are continuously changing the inner components of the battery itself. The major components are the same, but the chemicals inside the electrolyte, the liquid, is what's changing, and we'll touch more on that. So here is a little bit of what's inside the battery. The next picture will be better. It's an animation, but you have the negative side, which is the anode. Then you have the separator in between, which is very thin nowadays, and now you have the positive side, which is the cathode. So then here you have the lithium-ion particles, if you want, or molecules, or atoms, and they swim from one side to another. They go through the separator, and they're swimming in a liquid called electrolyte. And this is the liquid that explodes, or flammable. So in this animation, as you can see, the lithium ions are swimming in that liquid medium, which is the electrolyte, from one side to another. So if you're charging, they're flowing from the positive side to the negative once they're fully charged. And then when you're discharging, meaning you're using your device, then they flow the other way. So the current technology we have today, we must have this liquid electrolyte inside that battery that can make lithium-ion batteries work. The industry is working with different type of batteries, but until today nothing is as efficient as a lithium-ion battery. The problem occurs is when there's an abuse factor on the battery itself. The abuse factor we're going to be talking about in this presentation is overcharging and overheating. Overcharging and overheating is an abuse factor that happens quite often, and which we can stop. Now there is also another abuse factor that can cause thermal runaway, which is an accident. I know there's an image of two cars colliding. I just want you to know that they build these batteries very strong against any collisions for it to actually damage the separator inside. Because again, once you damage the separator inside, that's when the positive touches the negative, and that's what creates your explosion or thermal runaway. And then, of course, direct penetration is another factor that can cause thermal runaway, however, because you're piercing the separator. However, we're not going to talk about these two. There's nothing we can do to stop a mechanical abuse, and that's very rare, okay? But we're going to talk about overcharging and overheating. So once there's an abuse factor, if nothing is done to stop the abuse factor, that's when the batteries go into thermal runaway. And once one battery is in thermal runaway, then they propagate to the other batteries, and that's when you have a situation that you need to mitigate. But let's try and understand how thermal runaway happens. So if you remember, we talked about this electrolyte, which is the liquid. And in short, when there is an abuse factor, which can be overcharging or overheating, either overcharging or overheating, when there is an abuse factor, that liquid will start turning into a gas. Once that liquid starts turning into a gas, there will be a pressure built up inside the battery. That pressure buildup will push a vent that is designed at the top of the battery, and that's only if you have a cylindrical type battery. We'll touch on the pouch later. So that internal pressure will push the vent open, and now you have the gases from this electrolyte going up in the space. The problem occurs is as the abuse factor is allowed to continue, the more you start converting this liquid into a gas, it will be generated much faster than how much it can be vented. So therefore, you're going to keep increasing the internal pressure, and by that time, your internal separator is going to crack. Once the internal separator cracks, that's when the positive side chemicals are going to touch the negative side chemicals, and that's how it goes into thermal runaway. So in short, one more time, the electrolyte, the liquid electrolyte, will start converting into a gaseous state because of the abuse factor, which is overcharging or overheating. And once it starts turning into a gas, it will start venting to the atmosphere. But then if the abuse factor is allowed to continue, and since you are generating more gas than how much you are venting, it will eventually catch up and crack the separator. Once the separator is cracked due to the rise in pressure, the positive will touch the negative, and you will have an immediate thermal runaway. Now, thermal runaway is an exothermic reaction. Once it starts, it will also generate its own oxygen inside the battery itself, and you can never stop that battery from burning. You can put it in a sandbox, but it has to burn itself out. Now, what causes that electrolyte to become into a liquid? We spoke about overcharging. Overcharging is a chemical process. That means the anode has too much current on the anode itself, and since it's touching that liquid, then it's a chemical process because of the rise in the current concentration. Then it's going to react with the liquid, and it's going to start changing it into a gas. This happens at low temperatures. Therefore, not every thermal runaway happens at a high temperature. Overcharging happens at low temperatures. I'm going to show you some examples. Now, overheating, think of it as you're boiling that liquid. So this liquid electrolyte, like you're boiling it, and then it starts changing into a gas. So one of them is chemical process, the other one is overheating or boiling that liquid. Now, this should not happen due to the battery management system. Every device, your iOS device, has a battery management system. When you charge your phone at night and you sleep, you're not concerned that your phone is going to explode, because once it reaches 100%, the operating system is going to discharge the charging itself. So we depend on the battery management system to prevent thermal runaway happening from an overcharge. The problem occurs, and hopefully not on your cell phone. Now, I just want to say, even though you still see the sign saying that it's charging on your cell phone, it actually disconnected the charging. It's just showing you that it's being plugged, but the charging, the actual charging, had stopped once you reach 100%. Now, the battery management system, when it comes to bigger systems like in data centers and when it comes to energy storage, has so many variables that it's looking for. And what's been happening is that some of these variables can go wrong, and as a result, you end up having a thermal runaway. So no one is arguing that the battery management system should not be present. It's very, very important. However, despite the battery management system, we're still having incidences of thermal runaway, and that could also be due to a manufacturing defect either in the battery management system itself, or maybe in the battery itself, where the fuse inside the battery did not close once it's fully charged, and as a result, the battery kept taking more charges, and the voltage fluctuations on the module itself, since it's monitoring a lot of batteries, did not realize that there's a voltage fluctuations, and as a result you ended up with thermal runaway. So for that reason, it's unfortunate we're still having situations like this throughout the world. Again, they don't happen that often, but they are happening, and we need to have a separate system that can prevent, that can be redundant to the battery management system. We need to have redundancy, so in case the system fails, then we have something outside, just like we do in boiler rooms. These boilers, they come with safety features that it will shut down the intake on the methane in case there's a problem, and then maybe on the carbon monoxide on the exhaust. But we still have carbon monoxide and we still have methane detection in these boiler rooms, because you need an external system to still monitor that in case the battery system fails. The Arizona fire, it was sad to see. Even until today, we still have some firefighters, maybe one or two, I'm not sure, that still have not gone back to work ever since April 19 of 2019 due to that incident. And that was a thermal runaway that took place, and I will explain precisely how this explosion happened by showing you some charts on how methane accumulated inside, and that's what caused the explosion. But you will also learn that not all batteries release methane or L.E.L gas, so we're going to learn about that. And then, of course, fires in South Korea had stopped until this year. From 2017 and 2018, they had multiple fires in energy storage, which they used in buildings, just like we use in data centers. Data centers are inside buildings for us. And one battery went into thermal runaway, and I'll show you a video of what happened in South Korea. And just recently, I would say about 4 weeks ago, another incident happened in South Korea on some Samsung batteries as well, where the battery management system again failed to see a condition or the precursor warnings to thermal runaway. And then, of course, we're all consumers. We've seen many devices that go and explode, including some events on Boeing 787 and so on. So let's try and understand the battery failure stages and how we can stop it. So the battery stages happen in 4 stages. First, as we discussed, is the abuse factor, which is overcharging and overheating. In this here, you will see thermal, which is heating, and electrical is overcharging. There's nothing we can do about a mechanical abuse. Now, if you have overcharging and overheating, that abuse will start turning that liquid inside the battery into a gas. Once the internal pressure rises, it's going to start off-gassing to the space. This is the preventative region. During this region, this is where we can actually stop the charging and prevent thermal runaway from occurring. The problem occurs is if you keep the abuse factor going. Meaning, if you keep the abuse factor going, now the internal pressure is rising, and just about here, the separator is going to crack due to the rise in pressure, and by that time, the positive is going to start mixing with the negative. At the very initial stages of that mixture, you're going to start having a little smoke happening. And by that time you get to smoke, it's already too late, because what causes smoke is the cracking of the separator itself, which means the battery had cracked and failure is imminent by the time you get here. So then from smoke you go immediately to fire. So and then of course the 4th stage, like I said, is fire, and that's when you have propagation. I'm hearing some noises in the back, so maybe you can put your microphone on mute, and this way it'll be a nice recording for us here. So finally, how can we prevent this from happening? We need to monitor these off gases in the air, and we need to shut down the equipment, which is the abuse factor, whether it's overcharging or overheating. And then finally, we need to still monitor for smoke, not because we want to monitor smoke at the battery level here. We're monitoring for smoke from other devices that might cause fire. So if it's a server in a server room, in a data center, that causes fire because the components are very hot and they catch fire, whether it's a faulty wire, you need to monitor for smoke, which is also required by standards and codes. Okay? Off-gassing is not. Even though I'm on different committees, now they're talking about off-gassing, and they're going to be requiring off-gas monitors. We're going to touch a little bit more on that. Now, if you remember, on my second slide, I said this industry is still premature. The reason why I said it's still premature because different battery manufacturers have their own recipe of that liquid electrolyte, which is what the lithium ions are swimming in. So once you start having that abuse factor and you start turning that liquid into a gas, the gases that are emitted into the air are different from one battery manufacturer to another. So some are showing that you need to monitor for CO2. Some will tell you need to monitor for a combination of CO2 and hydrogen, and some for CO, and so on. However, I can tell you, and I'm going to show you some data, that even if you monitor for all of these gases, you will not be able to stop thermal runaway. And it's very simple. The conventional type gas detection is looking for certain readings that are specifically meant to protect people and against a lower explosive limit. They are not meant to look for very small levels of these gases. So the 25 parts per million on the carbon monoxide, that's when the sensor is going to alarm. That might be already thermal runaway on a battery. You cannot look for 25 parts per million. So you need to look for much lower concentrations. And what you're going to learn in this presentation, that even these gases are released at very low levels initially. And what's being released is something else in the beginning, and that's what we're going to be talking about. But in general, if you want to be able to detect the off gases, you need to monitor not just one specific gas. You need to monitor the blend or the cocktail of these gases. And that's what we need to be looking for in order to successfully detect thermal runaway. Now, this technology is a technology that was developed for our U.S. Navy. I was doing a presentation last week with authority having jurisdiction in Hawaii, and the same people that I was actually talking about an incident that happened in Hawaii and how our U.S. government decided to study how lithium-ion batteries fail. One of the firefighters was on the call, and he said, "Yes, this is an incident that I actually witnessed, and you're right about that." So what happened is this: a submersible vehicle had lithium-ion battery that the Navy was using, and one day they were charging the lithium-ion battery off the submersible vehicle. And what ended up happening is it caught fire, and the fire really scared the Navy. So then they had a government project to try and understand how lithium-ion batteries fail. The company we aligned ourselves with won this government project, and they started doing the research into why lithium-ion batteries fail. And then 2 years after that, they presented the information with the government, which is similar to what I discussed with you about the 4 stages and the off-gassing and the type of gases that are also released and how to stop it. So then the Navy asked them, can you develop a system that can actually stop it? And they did. After 6 or 7 years, they did. And then the U.S. government said, okay, now you can go ahead and commercialize it. And now it's being installed on every Navy platform. It won several awards in government agencies like the Advanced Research Project Agencies, Chemical Society of Engineers, and the Salt Lake City and Solar Plus City. And then the most important thing is that it also being used with energy storage companies. Unfortunately, in California, nobody's mandating it simply because they want to save, even though it's really less than 1% of the total project. So some projects in California are having it because we're dealing with system integrators that got exposed into thermal runaway before, and their reputation was on the line, so they decided to have this type of detector, so this way they don't have any thermal runaway going forward. In many counties or cities within California, it's still not being implemented. So Duke Energy is one of the big energy utilities in the U.S. They will not have any energy storage without having the off-gas monitor. Now, it was also recognized by the Maritime Battery Safety, which is a joint development program that was looking into how we can protect against lithium-ion batteries in general for safety reasons, and also how we can mitigate the risk if an explosion was to happen. So they had third-party people involved in this, and they purposely made these batteries fail, and then they had different type of detection technologies out there. And this is what their conclusion was, and many insurance companies were on this as well. So they said the L.E.L sensor and voltage do not provide a mechanism for early warning. In comparison, I have changed the language so I don't have to specifically say the company's name, but they were saying in comparison, the off-gas sensor indicates only seconds after off-gassing occurs. In addition, testing was performed where the cell was being overcharged and charging stopped when the off-gas released, and as indicated by the gas monitor, by the off-gas monitor. So what they're saying, they had our off-gas monitor in the space, and they had many other sensors as well, and our off-gas monitor detected the off-gas in the air, and then it immediately sent a signal and it shut down the equipment, and that's when they said the cell temperature ceased to increase and the off-gassing started to decline until the cell was considered stable. Now, when they say considered stable, it did not go into thermal runaway, but you still cannot use that cell anymore. You have to discard of it and get a new cell. This cell is considered defective now. Otherwise, you'll still go into thermal runaway. So then they said, meaning early detection coupled with the correction system shutdown measures is an important safety barrier. So when it comes to regulations and regulatory parties, we have NFPA 855, which is the standard for the energy storage systems, and we also have NFPA 75. I can tell you NFPA 75 is moving to start requesting an off-gas monitor, and when I say an off-gas monitor, you need to look for the cocktail of the gases, not a specific gas, and I will show you later why. Now, they added into the index or the appendix that off-gassing is one of the approved method to monitor for that. They also added that a battery management system should be one of the methods. So they're telling you this or that. However, it still needs to work, and because a battery management system is always going to be offered when you have lithium-ion batteries, and explosions are still happening, so we cannot simply depend on them. So we need an external system. So here they recognize that we need off-gassing, but at the same time they're saying a battery management system is also okay in a way. And what we're saying is battery management systems are always going to be there, and it's still happening. You need redundancy. You need something in addition to that. And I think it's happening because there are many people on this committee that now they are convinced, including a battery management system manufacturer, meaning a software company that is on the board, and they finally now agree that you need an external protection, and they sit on this committee, so this is huge. And it took us a while for us to convince them after we showed them many testing data. So we're there, but we're not fully there yet. UL 9540A is a test method. No one can buy or no one can sell a lithium-ion battery without actually testing it with UL 9540A. Now, what is that test method? It does not have a passing grade or a failure grade. This test method will test the cell by purposely making it fail and overheating it, and then you purposely make it fail in a module, and then you purposely make it fail in a rack, and then you record the performance criteria for that system. You record that for that battery type, at what time it off-gassed, at what temperature, and at what temperature the thermal runaway happened, and at what time. Then you generate a test report that you can share with the fire consultant companies or the manufacturer of the battery itself, and that report can also be shared with insurance companies, building owners, authority having jurisdictions, and fire departments. So if you have a project in your jurisdiction, and for example you know that they're using Samsung batteries or LG Chem type batteries, you can call UL 9540A as an authority having jurisdiction, you can call them and you can request, or a fire consultant perhaps, and you can say, I have an LG Chem type battery for this type of project that we're working on. I would like to have your test report that you conducted for this type of battery, and then go ahead and ask them, was there an off-gas monitor present during the times you did that testing? Because I can tell you for sure that on many occasions the off-gas monitor was present, and then the data was collected whether it detected the off-gases prior to thermal runaway or not, which means you would know whether it can stop it or not. So are we there yet? Not entirely, but I can tell you 3 big major insurance companies are actually adding the off-gas monitoring requirement to their jobs, or the projects that they insure. I'm not sure whether they're going to be able to reinforce it or if people can get discounts if they offer it, but it's happening. So the awareness is ongoing. Authority having jurisdictions are mandating it. Some of them. I was requested to type a city ordinance as an example, and to send it also to the people I'm working with in 2 places, in Florida and also in Hawaii. So again, if somebody is on this call that would like a city ordinance, I do have an example to provide that. Developers and system integrators are starting to include it. Some of them, the ones that actually either being requested by the insurance companies to provide it, or the ones that had a thermal runaway incident and they don't want to have this again, so now they're asking for it. And of course, some utility companies are demanding it. Not everyone, but some are. So we're not there yet, but we are growing this awareness. Now, this type of battery released carbon monoxide, methane, ethane, and ethylene. This was conducted by the third-party testing for that DNV GL. We do have that report available, and it's online. If you take a snapshot and you can type DNV GL report, you can download the PDF, but we can send it to you. This was due to an overcharge. If you remember, I said an overcharge, you don't get a temperature rise. It happens at low temperatures. And it's relative. I'll show you what the temperatures are. But as you can see, carbon monoxide for this battery type only, carbon monoxide, methane, ethane, and ethylene was released. But look how low the levels are. So your conventional type gas detector will not sound the alarm. And if you were to lower the alarm levels, I've been in gas detection for 15 years, and I used to work for a gas detection manufacturer, and I could tell you that even if you were to lower the alarm levels into parts per million, or L.E.L, the sensitivity of the sensing element itself is we're not sure it can actually give you an accurate reading. So there's a dead band in some detectors. A dead band is when you will not start reporting until you get to a certain level. That's because the technology does not exist in the sensor itself to start reading at a very, very low levels. In some cases, you might need an analyzer. So as you can see, this was due to an overcharge, which is the excess current into the battery, which is a chemical reaction. Because you have excess current in the battery, it will start changing that liquid into a gas. And the off-gas monitor here detected the off-gas early on, and then the device was disconnected and it never went into thermal runaway. So thermal runaway was avoided. So you can see that the temperature was 45 degrees Celsius. 45 degrees Celsius is 114 Fahrenheit. This is normal for a battery. There are no thermal runaway due to overcharging, due to heat that are reported at this temperature. So the operating system might think this is just a normal temperature, so they would only focus on the voltage fluctuations, not the temperature in this incident, because the temperature is not going to reveal anything to them. When I charge my phone and I touch my battery in the back, the battery is super hot, and I know it's in 100, 110, maybe 105, I'm not sure, but I know it's very hot. So 114 is normal. And I only show this example just to show you that thermal runaway can occur at a low temperature, because this is a chemical reaction that turns the liquid into a gas. Now this one is overheating, and we've conducted this experiment to a customer that has battery of their own, and we heated the battery at 5 degrees Celsius per minute. And once we got to 25 minutes, the battery failed, meaning it off-gassed. Now, we did not stop charging because we wanted to, or we did not stop heating the battery because we wanted to see how much of an early warning we can get to show the customer that how much of an early warning. So once it started off-gassing, we kept the abuse factor going, and at 36 minutes, that's when the battery caught fire, which means the separator was cracking or cracked, melting down, and then the positive is mixing with the negative. You started getting smoke. That's when the smoke detector went off, and then of course immediately followed by fire. So the early warning in this instance was 11.6 minutes, and that's what the Korean call the golden time, once they understood how batteries fail. Now in this example, it's the pouch type, and I'm showing you a picture here. The pouch, that's how the gas or the liquid inside, when starts changing into a gas, that's how it builds up inside. Now, unlike the cylindrical shape, we don't have a natural vent that can open for the off gas to start being released. So we depend on the seal of the bag itself to break. So the seal will break from one point, and then the off gases will start going to the space itself. In this experiment, again by third party, they started heating the battery on purpose. They wanted to see if the off-gas monitor can detect it, and right here the seal broke, and now you have the off-gas into the air. But the warning was about 6 minutes, so they wanted to see how long the warning was. So after 6 minutes or so, it went into thermal runaway. Now in this example, the same type of battery, the seal broke, but in this example they actually wired the controller back to a disconnect switch, and as soon as the off-gas detector detected the off-gas, it immediately shut down the charging or the abuse factor, and then the battery never went into thermal runaway. So that shows you even in 6 minutes or under, you can still prevent thermal runaway. Now, we are advising the industry that they can perhaps build a weaker spot on the pouch type battery, so that when you start accumulating or generating the off gas inside the battery, the weaker spot will break, and you can get a much higher warning than 6 minutes in this examples. But the pouch type, we've registered anywhere between 2 minutes to 6 minutes in warning, and in all of these incidences we were able to stop thermal runaway from occurring. Now in this example, I want to show you, this is the battery type that is being used, can generate carbon monoxide, methane, and ethane. And as you can see, the levels are extremely low, so the conventional type gas detector will not pick it up. Notice how methane only spiked really high once the battery went into thermal runaway. Now that's one battery, so you don't have a lot of methane in the space, but still, this is an indication that only when the battery goes into thermal runaway, you start having a much higher methane concentration. So if you're going to target and look for methane at this level, or CO, carbon monoxide, you won't be able to prevent thermal runaway because they only go up high just prior to thermal runaway. Now in this battery type, hydrogen chloride was released, hydrogen fluoride, and hydrogen as well. And notice that we had also an L.E.L type detector, not us, the third party testing as well, had an L.E.L type detection, and the L.E.L detector never even picked it up. So the NFPA 855 now also recommending having an L.E.L detector ever since the Arizona incident, and I will comment a little bit on that. But it's not to prevent, they do say it is not to prevent thermal runaway, it is only to protect firefighters in case of accumulation in methane after thermal runaway had occurred, in order to protect them from this zone when you have methane in higher concentration, but not before. Because look, before you didn't even detect it in this type of battery, it didn't even release that. So look here, even hydrogen was released very late, only once it started going into thermal runaway. Nowadays, I'm being honest, so there's another Honeywell company in Germany won a project in the energy storage, and they are monitoring hydrogen, CO and hydrogen for that project. And I used to work for that same company for 15 years. And I can tell you right now that they think it can stop thermal runaway. We know it cannot, because when we did this merger, Honeywell has many companies. We've tested so many different testings and scenarios, and we knew you need to monitor for the off gases altogether, the concentration of all of these gases in order to stop it. But here is something else that I haven't mentioned. The initial failure is looking for volatile organic compounds. Volatile organic compounds is the common denominator in all of the battery types. These batteries use these solvents inside the electrolyte. The electrolyte is the liquid inside in which these lithium-ion atoms are swimming in. Once they start failing, or once you have an abuse factor, they will start releasing or changing into VOCs, volatile organic compounds, along with these gases. Okay, but these gases are not in high concentrations, as you can see. So in order to detect and successfully determine that there is the conditions that are occurring for thermal runaway, you need to monitor the VOCs along with some other gases altogether, which is the volatile organic compounds. And that's why the off-gas monitor is always on almost every battery type. It's almost capable of detecting and preventing thermal runaway of happening. So what happened in the Arizona fires at APS? Obviously, we know that there were methane levels started rising very high. So we know they were using this battery type or a different battery type that can give you the combination of methane, carbon monoxide, and maybe hydrogen. We don't know the battery type, but I can tell you it's probably this battery type due to how much methane it has. Initially, it had thermal runaway, and thermal runaway, then it propagated. The space did not explode, but now the space was filled with methane. So the batteries were on fire. It kind of filled the space with smoke, and methane was very high in that. So you went from an area where it will support combustion into an area too rich for combustion. But you did not have that explosion when you jumped from here to here, because the explosion was happening at the battery level. And if you remember, I said methane will start happening later once you have thermal runaway. So then the environment became too rich for combustion. When do you get too rich for combustion? Well, if you have the perfect concentration between methane and oxygen, you will be in this zone. And then in this zone, it will support combustion if ignited. So in those movies, when they show you somebody's fighting in the kitchen, and then they take the propane, they release the propane into the space, and then they throw a match, and then the entire house explodes. In reality, it will only explode if you are in this zone, and this zone will call for a perfect concentration of the L.E.L gas and of oxygen in the air. So if you are in that perfect zone, it will support combustion if ignited, and it will explode to give you this. Now, when you're at the initial stages, it's too lean for combustion. You don't have enough of that gas. Now, if you keep on releasing gases more and more, then it becomes too rich for combustion. And that's what happened in here. When the firefighter opened up the door, now that you were after thermal runaway, now that the space is filled with methane, the minute they opened up the door, oxygen rushed inside. And once oxygen rushed inside, you became in the perfect concentration between oxygen and methane, and immediately the space went into an explosion. And that's what happened. And that's why NFPA 855 now recommends having L.E.L detectors, and they indicate just to protect against another condition like this, so that when you open the door, you don't have air coming in, rushing, and then you have a perfect condition for an explosion. However, they recognize that it will not stop your thermal runaway in the battery. So what we need to do is to stop it from even occurring, so that we don't have to mitigate later. I mean, we can mitigate, of course, but we can minimize that risk by having an off-gas detector. And we also have to recognize that not all batteries are going to release methane like we've shown you before. So here's a video that shows you how the off gases look like. It's hard to see, but it's like sparkle. think of some liquid spray being sprayed in the air. So once you have the internal pressure rising and that liquid changing into a gas, it's going to be mixed with some droplets of that liquid, and what's going to happen is it's going to be pushed through the vent to the outside. And at that time, you're still in the off-gas zone, which means the separator itself is still intact. Nothing had happened to it. So keep looking in this zone and you will see that sparkle. So you do realize that by the way, I know you can't hear the video, but feel free to request that video and I'll send it to you. So look again at the sparkle, and that's when the vent opens and it pushes the air one more time, pushes the gas. And that's your sparkle right there. That's your off gas. And at that time, you don't have any COs. I mean, you have a combination. You might have some hydrogen in there and the VOCs, okay, volatile organic compounds. Now, can the detection also look for CO and methane and all of these gases? Yes, but the majority of these gases are volatile organic compounds, and that's what's being released into that space. And now we're going to look into the smoke stage. So if you keep the abuse factor, now you're going to go into the smoke phase. Of course, I'm showing you this video, but smoke had erupted much faster now. The initial stages, let's say if you had a VESDA system in there, might detect it much early on, but even if you detect it way too early, that means the separator cracked, and by that time failure is imminent. So let's look how fast we go from smoke to fire. So in this situation here, that was an energy storage facility, and it did go to fire, and that's what happened to the facility after that. And it's unfortunate, but it burnt down completely. Okay, so that's what we need to be able to avoid. Now, and that's the energy storage on the outside. Now, don't let batteries discourage you. We use them every day, and they're safe. All what we're saying is eventually 1 in a million, or eventually you might have an incident like this, which is why, I mean, we have devices in our own home that can cause fire, and that's why we have smoke detection in there to alert us. But we also have a system that can alert you to the conditions that can prior to the thermal runaway, which is the off gas, and not let it go to smoke and fire. In this way we can prevent everything together. So this is one cell test. We let it go all the way. One cell has so much energy, it just has to burn itself out. I just want to show you how much one cell can have in terms of energy. And that's one cell. So here's another test example that was conducted for a customer. They have their batteries in there, and there are battery modules, and we had an off-gas monitor in the front. The minute the timer starts, just like now, that means the off-gas monitor detected the off-gases. So we purposely abused the battery to try and see how much of an early warning we can get for that customer before the battery goes into thermal runaway. And you'll see when the timer stops, you'll see. So in this example, it was 11 and 37 seconds, and that's when the regular smoke detector went off as well. What we want to do is to be able to detect the off gases at the rack level, depending on the design, and we're going to talk quickly about that, because sometimes if you have two racks facing one another and the hot aisle is here, meaning the batteries are being cooled from the back to the front, and then from here to the front, and they're both joining the center, that means you could have detectors that are joined between the two racks, and this way they can minimize cost. But the idea is to send that signal to the controller, and then from the controller it goes to the fire panel, and then from the fire panel you can disconnect power, and in some cases it can go directly to the building management system or the battery management system. So that's what you want to do. Now, when it comes to renewable energy, we know how it is. We tap into the power from wind and solar, and we store all that in batteries for later use, so that the utility company can switch from fossil fuel to batteries. And eventually, once we have enough, it will switch from battery zone A to battery zone B to C to D, and then back to A once A is fully charged again. And that's what we call fully independent of fossil fuel. Inside each containers, it depends on the job. Nowadays, some companies are designing containers a little bit much smaller as well. And you want to have one detector per rack, or you can have one detector joining two racks if they are facing one another in terms of the hot aisle. Some system integrators or factories are designing it this way, working directly with us on that. So if you have in data centers, we force the air to come from, to cool the batteries. So if it's coming from the back to the front, you want to have the detector on top facing down, or put it in the airstream so it can be detected immediately. If it's coming from the top to the bottom, then put it on its side facing down, either direction, because you don't want any dust particles to go inside the sensor. And then, of course, if you have from the front to the back, you want to have the detector on top facing down as well. And then from the bottom all the way to the top as well, you want to have the detector facing down. So so in terms of design, I mean, it's really easy. You just want to put it in the airstream, and there are ways to minimize the quantities of the detectors itself. So where are we today? I can tell you, I submitted a comment yesterday. It was the last day to comment on NFPA 855, and I can tell you there are industries within 855, software industries building battery management systems, are realizing that, hey, you know what, it's not an insult if we add an external system. So they're realizing that, but we need to have a standard and a code to actually force it. So we're not fully there. L.E.L. will protect firefighters for the batteries that will release methane after the thermal runaway or the off-gassing had occurred, not before. We need to be able to stop it before. So this is still work in progress, but we're 2 years away. And this is an industry that's changing every day. To wait 2 years until they revise the codes is just simply too long. Same thing for NFPA 875. They're working on that, and it's going to take 2 years again before it's changed. So our preference is to have some sort of city ordinance, like some people requested that on their own, where you can say, if you're going to have this in my jurisdiction, then you need to provide an off-gas monitor, at least in data centers. I mean, if you're not concerned about energy storages, at least in data centers. The problem is it's going to become challenging when you start having these fires inside data centers in buildings that are on the 4th floor or maybe on the 17th floor, downtown buildings, and now you need to put off that fire. Just be aware that it's being changed, just like they call authority having jurisdictions in New York. They say, just like thieves in the middle of the night. That's how they're describing it, that they're changing the lead acid type to lithium-ion. And you're going to hear many things. You're going to hear people telling you, yeah, but that lithium-ion, it's lithium-ion phosphate. Well, lithium-ion phosphate will also explode. Some of them will have more controlled explosion. As long as you have a liquid combustible inside the battery, it will turn and go into fire. Okay? So as long as you have that. So just remember that. Because they're going to throw you off by talking fancy in terms of the different battery types. We've tested many battery types, and they all go to flames. All right, so in review, this is a technology that was specifically built for our U.S. government, and we're proud of that. It's being installed on every Navy ships today in terms of protection against lithium-ion fires. The stages are abuse factor. Then from there you get to the off-gas phase, and right at that stage, this is where you need to shut down the equipment and stop the abuse factor. Otherwise, it will go to smoke and fire, where failure is imminent. And that's my presentation for today. I am open for questions now and any type of support, and please let me know.